Hey students, this lesson is 7.6. It's about exponential functions. In this lesson, we're going to learn how to evaluate and graph exponential functions. Go ahead and do the review here, and I'll check back with you. All right, an exponential function is a function of the form y equals a times b to the x, where a is not equal to 0, b is greater than 0, and b is not equal to 1, and x is a real number. So, and here's what they look like when you graph them. If all of the x values in a table have a constant difference and all of the y values have a constant ratio, then the table represents an exponential function. We'll talk more about that in a second. All right, it says, does the table or rule represent an exponential function? And let's do B first. It said that if we can write it this way, where A is not equal to 0, B is greater than 0, and B is not equal to 1. And then X is any real number. So, and I think this one we can write that way. So we're going to just do that like this. So we can write it as 1 times 2 to the x power. And so it fits this form. So we're going to say, yes, this is an exponential function. All right, this other one here, we're going to check the ratios. If x goes up by a constant amount and y's have a constant ratio, in other words, if we do 6 divided by 2, we get 3. And then we do 10 divided by 6, and that is equal to 1.6. And then we do 14 divided by 10, and that's 1.4. Notice we don't have a constant ratio. In other words, there's no number we're multiplying by to get the next number. That's the same. So the answer to that one is no. It's not an exponential function. Actually, it's a linear function because we're adding the same every time. Keep adding 4. All right, you try that. All right, evaluating exponential functions. So suppose a culture of bacteria doubles each hour. There are initially 2,200 bacteria. The function f of x equals 2,200 times 2 to the x gives the number of bacteria after x hours. How many bacteria will there be after 5 hours? So x is the number of hours. You see that here. So we're just going to find f of 5, and that's 2,200. Times 2 to the 5th, and we can use our calculator to do that. So we're just going to multiply 2,200 and use the exponential function on our calculator. And that's equal to 70,000. So that means that in 5 hours there will be 70,400 bacteria in this culture. All right, you try that. All right, to graph an exponential function, we can just find some values and put them in, make a table, and then graph them that way. So let's go ahead and do that. I'll make a table of values, and we'll just find for the first few inputs here, we'll go from -2 to 5 and see what happens. And I'm just using my calculator to find these values. I get about 0.28, so this is just a really small number. If I put -1 in for the power, I get 0.083 repeating, I put in 0 for the power, of course, anything to the 0 power is 1, so I'm going to get 0.25 when I do that. If I put in 1 for the power, that's 3. 3 times 0.25 is 0.75. And then 0.25 times 3 to the second is 2.25. 0.25 times 3 to the third, that's 6.75. 4 and 5, I'll finish those up and then we'll graph them. Notice that initially the line just hugs along here, and we know that it will never be a negative value because if we keep dividing a positive number by a positive number, it's going to stay above 0. But eventually it starts to really take off, and so it makes a curve that looks like that. All right, you try that. To help me decide which graph goes where, I knew that this one here had to be one that was really growing, going up as x got greater, an increasing graph. And I know that multiplying by a positive 1/2, that would keep getting smaller because you keep taking 1/2 of that, but it would always stay positive. And then I just used the idea that if it's a negative of that, it's just going to be that function flipped over to find my other two values. All right, graphing an exponential model. Suppose an investment of 7,500 doubles in value every 12 years. The function f of x equals 7,500 times 2. That models the growth of the investment where x is the number of 12-year periods. So we're going to make a table and graph this. And so we'll put x here. And since it's years and it's 12-year periods, what I think I'll do is change our scale in the graph, and we're going to go by numbers like this. So after 0 12-year periods, of course, I'm going to be at where I started, 7,500. After one 12-year period, that doubles. So that's 15,000. After 2, it doubles again, 30,000, 60,000, 120,000, 240,000, and 480,000. Now that 6 12-year periods, so that is 72 years of this investment. Okay, so we have to pick a scale here. What we're going to say is that this is in 10,000s to make this work. So 50 10,000s is the same as 500,000. That will fit that. So this is the value here, and this is the number of 12-year periods. Okay, the first 12-year period, or the 0 12-year period, is way, way, way down there. The first one is at 15,000, which is a little before 20,000. Then we have 30,000, which is right there, 60,000, 120,000, 240,000, and 480,000 in the end. And our money just keeps growing exponentially. All right, try that. All right, looks like we're at the lesson check. Go ahead and do that and be ready to talk about that next time we meet in class.